The first law of thermodynamics says that we cannot create or destroy energy. So the amount of potential chemical energy in the reaction at the beginning is equal to the amount of energy at the end. The problem is that not all of it is energy that we can use in a way that we want. So if we have a combustion reaction, some of that energy goes to propel the car forward, around 20%. The rest of that energy is dissipated as heat, which we can't use to move the car forward. So no matter what we do, we can't win. The second law of thermodynamics states that although we can't win, we can't break even either. So there is a heat tax for every step that we go in our conversion of energy. So if we look at heating our house with electricity, if we burn, most of the electricity that we get comes from burning fossil fuels. So if we burn the fossil fuels, there's heat that's given off that can't be used to make energy. That energy from the heat goes to producing steam, and we make steam. We lose some of the heat as we go to the generator to generate our electricity. As we transmit that electricity through the power lines, there's a little bit of the energy that's lost as heat. And then if we heat our houses with electric heat, there's still more heat that is lost that is not producing heat. So in this case, it's producing light on the elements that are used to produce heat. However, if we heat our house with natural gas, that is burning a fossil fuel from the start. We do have a heat tax there, but then most of that energy can be used as heat. So the less steps that we take, the more efficient our conversion is. Thermodynamics helps us to predict whether or not a process is going to occur under given conditions. So any process that occurs without having to put in outside interventions or outside forces is called a spontaneous reaction or spontaneous process. If we want a non-spontaneous process, we have to put energy in to get that process to happen. So it's not that they're impossible, but it does take external energy to have non-spontaneous processes. And so a spontaneous process is irreversible because there's a net release of energy when it's proceeding. So an example of that is if you have a car, spontaneously the iron in the car, when it reacts with oxygen, produces rust. So without any external forces, the iron is going to turn into rust. The non-spontaneous process would be turning that rust back into iron. So we would have to put in some energy to get that to occur. If the process is spontaneous in one direction, it has to be non-spontaneous in the opposite direction. So then it's going to require the input of energy. So turning diamond into graphite is actually a spontaneous process. So diamond is going to convert into graphite because it's more stable. But this process is very, very slow. So the kinetics of it are not on a time scale that we can observe. So you don't have to worry about the diamonds that you buy turning into not worthless, but less valuable graphite in generations. So we can think about kinetics as the speed of the reaction. So the kinetics of our reaction gives us information about how fast it's going to happen. The thermodynamics tells us how spontaneous the reaction is, whether or not it's going to travel in that direction or occur spontaneously. Let's think about some processes that we already know. Okay, we know that systems with higher potential energy tend to move towards a lower potential energy. So if we think about this in terms of enthalpy, right, the heat of a reaction, most spontaneous processes are exothermic. They give off heat. We're going from a higher energy level or a higher energy system to a lower potential energy, and so it gives off its energy as heat. But we do have some spontaneous processes that are endothermic, things that we have to put heat into and they still occur spontaneously. So one example of that is ice melting. So ice melts if we are above a temperature of 0 degrees Celsius. Now the reason that ice melts, even though it requires the input of energy, is because we are moving from very organized water molecules in a crystalline structure to liquid water, which is less organized. So there's more freedom of motion, there is more randomness, more disorder, and this is what we call entropy. So it's not just the enthalpy of a reaction that's important, there's also this idea of entropy or disorder that occurs. Water evaporating is another example that we can look at. So liquid water has vibrational, it also does move some, but when it evaporates and turns into a gas, those molecules have a lot more freedom of motion. The disorder or the randomness has increased when it becomes a gas. That means that the entropy has also increased. The second law of thermodynamics looks at entropy. So entropy is represented by S. And so the second law of thermodynamics states that any spontaneous process that occurs, the entropy of the universe has to increase. And so that means that if we're increasing the disorder, increasing the randomness, then our process is going to be spontaneous. Entropy is also a state function, so just like enthalpy and energy that we looked at in the first semester general chemistry, it only depends on the final and the initial state. Doesn't matter how the molecules get to those places, but just what those states are in the final and the initial. So that's why we have the delta. The delta represents our state function. There are two factors that we have to consider for a spontaneous reaction. So one is the enthalpy, and the other is the entropy. So remember, enthalpy, delta H, is our change in energy plus the pressure times change in volume. This is the heat of our reaction. So delta H is equivalent to the heat of our process or the heat of our reaction. Delta S is the difference in randomness or disorder of the reactants compared to the products. And so if we're increasing the number of energetically equivalent ways of arranging those components, then we're increasing the entropy. Entropy is S, and the units for entropy are joules per mole Kelvin. If we think about salt dissolving in water, okay, so salt is a very ordered crystalline structure of sodiums and chlorides alternating. If we put it into solution, that salt now is more randomly dispersed. Those sodium and chloride ions are more randomly dispersed within the water, which is an increase in entropy. If we think about state changes, so we've already talked about solids, liquids, and gases. So in a solid, we have vibrational energy. So our molecules are vibrating within their crystal structure. If we add some energy by increasing the temperature, we're also increasing the entropy. So once we move from a solid into the liquid, those molecules are able to move around more freely. We've increased their freedom of motion. If we move into the gas phase, now we have rotational energy, so the molecules can spin around. We also have translational, which means that they can travel in straight lines, and we've greatly increased the amount of entropy that those molecules have. Predict whether the entropy of the system is increasing, which would be positive, or decreasing, which would be negative for each of the following situations. Pause the video and try to decide which they would be. So water vapor, we're taking a gaseous water and condensing it into the liquid. So in this case, our disorder, our randomness would be decreasing, would be negative. Okay, things are becoming more ordered. Separation of oil and vinegar, salad dressing. Okay, so as they separate out, things are becoming more organized, and so our change in entropy, or delta S, is negative in this case because things are getting more organized. They're separating out from each other. How about sugar dissolving in tea? Well, in this case, our delta S, our very crystalline organized sugar, is dissolving, becoming more random, moving into the solution. And so in this case, our delta S is positive. Well, now we have some chemical reactions. So we've got lead 4 oxide becoming lead 2 oxide and oxygen. Our delta S for this one is positive. Why would it be positive? Well, we're going from a solid to a solid and a gas. So because we're getting the gas, that's less organized, and so our delta S is positive. Okay, now we have ammonia becoming nitrogen and hydrogen. All of these are gases. So what about our delta S? So our entropy, we're going from 2 molecules of ammonia into 4 new gas molecules. And so this is going to be positive. How about silver, the silver ion and the chloride ion in aqueous solution becoming a solid? Well, in this case, we're going from them being distributed throughout the solution to becoming a solid, which is crystals. And so in this case, our delta S is negative. So you can kind of think about this as, say, your bedroom. For your bedroom, it's pretty easy for things to become disorganized over time. You're increasing your entropy as things are organized. You have to put some work in, some effort in to keep things organized in your bedroom. And that's kind of how entropy works as well.